All right, let's go on and talk about section 6.2. In 6.1 we talked about some of the properties of tangents. In 6.2, let's move on. Let's talk about some of the properties of chords when we're talking about circles. Now I've already got circle C here on the screen for you, and I've already made two chords. Remember, chords connect two endpoints on a circle. So I've already got these two chords made, and I made these chords, if you look, I've got them measured out here. I made these chords to be congruent, no matter where I move it to. And if I change the size of one, I'm changing the size of both. So I am giving you the fact that these two chords are congruent. There's not a special property that relates or that makes these chords congruent, just the fact that I made them congruent. So they are always going to be congruent because of the way that I built them. All right? So if I start off with knowing that these will always be congruent, I'm giving you they are congruent, let's make some radii on this circle. And we'll make them to the endpoints of these chords. All right, let's shift, oops, didn't want that point on there. Let's shift this a little bit so we see it about like that. So if we look at it like this, it almost looks like a straight line. But if I move it up here, we see that those lines are not guaranteed to be straight. So the first thing I want to talk about, these chords are congruent, so the lengths are the same. What about the central angle that's associated with them? I could say that this central angle, angle FCG, is defined by this chord because the endpoints are making this angle. The radii to the endpoints of a chord are making this central angle. So I could say that central angle FCG is defined by chord FG. I could make a similar statement about central angle ECD. It is also defined by chord ED. So what can I say then about the central angles that are made here? Angle FCG and angle ECD. Well, let's take a look for a minute at what we have here with the chords. Again, it doesn't matter where I move them to. So they're still congruent chords. I know that segment CE is a radius, segment CD is a radius. Well, they are congruent because all radii in a circle are congruent. I also know segment CG and segment CF are radii. So they're congruent. But not only are they congruent here, they're also congruent to these. So I've got side to side. I've also got this side is congruent to this side. And I made my chords congruent to start with. We've still got the measures just to make sure. But I know that this side is congruent to this side. So by side, 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 these two triangles are also congruent. Well, my corresponding angles, the base angles, angle CFG and angle FGC, are congruent over here. So this angle is congruent to this angle. It's congruent to this angle. It's congruent to this angle. And all that's left to correspond is my central angle. Angle ECD is congruent to angle FCG. So my central angles are also congruent. There's my first property of chords, ladies and gentlemen. If my chords are congruent, then they define congruent central angles. The central angles they define are also congruent. So this angle is congruent to this angle. Now mind you, I haven't made any statement about these two angles. I don't know anything about them. Those central angles I can't say anything about. But here, the central angles that are defined by my congruent chords are in fact congruent. And let's double check it by measuring. We got this great tool with Sketchpad. The measure of angle FCG and the measure of angle ECD. Two central angles defined by two congruent chords, and they are both congruent. Every time, all the time, ladies and gentlemen. It doesn't matter where I move this guy to. The chord is still congruent. The central angles are still congruent. So what else can I say then? Let's talk about the arcs that are created or intercepted by these two congruent chords. I've got arc ED and I've got arc GF. First, let's measure arc GF. Well, if that's 94.6 degrees, why would that be 94.6 degrees? I think it makes sense because we learned that an arc's measure is equal to the measure of the central angle that intercepts it. So if I know that the measure of angle FCG is 94.6, then I know that the measure of arc GF is 94.6 degrees as well. So what's a good conjecture that I can make about arc ED? What's the measure of that going to be? Well, that one should be 94.6 degrees as well. And it is. So not only do congruent chords define congruent central angles, they also intercept congruent arcs. So if I know that chord FG is congruent to chord ED, then I know that arc ED has the same measure as arc FG. All right, so there's my first two properties of chords. Congruent chords determine congruent central angles, and they intercept congruent arcs as well. Now, for this next one, let me try to come in here and clean this up a little bit. I'm going to get rid of one of the chords. I'm going to hide it, and I'm going to hide some of those radii. And let's just look at, if I draw a perpendicular line from the center of the circle, from point C, to this chord, chord ED, let's see what happens there. What does it look like it does to that chord? No matter where I move it to, how I change the circle, all my other relationships are holding true. But what does it do if I drop a point right here at this intersection, where that perpendicular line, remember I built this to be perpendicular, so angle CHE is 90 degrees, it is a right angle. What does H do to chord ED? Well, it looks like it bisects it, doesn't it? Let's see if we can verify that. Let's measure segment EH. Let's measure segment HD. Look at that. This segment, HD, is congruent to segment HE. When I drew a line from the center, perpendicular to the chord, it bisected it. And it doesn't matter where I move that chord to, it's always bisecting it. Let's see if that makes sense. Let's see if we can figure out why that makes sense. If I put my radii back in here, actually I can just unhide them. Got a little too much for my money there. If I put those radii back on there, I know that this segment is congruent to this segment. And I know that I've made a right angle right here. And I also know, because it's an isosceles triangle, that angle CEH and angle CDH are congruent. On this bigger one, it's an isosceles triangle. Now, if I split it up into two right triangles, there are a number of ways to prove that this guy is the same measure as this guy, or that H bisects ED. Remember when we talked about the properties of isosceles triangles, if I drop from the vertex angle, if I draw the line perpendicular to the base, it bisects this angle, and it also bisects my base. So we could use something way back when with the properties of isosceles triangles to prove that it is the bisector, that H bisects ED. But we could also use I know that this angle is congruent to this angle, and that's 90 degrees. This radius is congruent to this radius. So I've got side, angle, angle. And side, angle, angle. So this smaller right triangle is congruent to this smaller right triangle, which means that my corresponding segments EH and segment DH are also congruent. So my third property of a chord is and this has to do with any chords, not just congruent chords, the perpendicular line from the center of the circle to the chord bisects it. It is a perpendicular bisector of that chord. So now, let's bring back my congruent segment over here. Make sure we're going to stay congruent, and we're staying congruent. Let's get rid of our radius here. I want to keep that point though. And let's construct a perpendicular to this other chord. So by what we just learned, this perpendicular line bisects FG. Let me clean it up a little bit. I'm not worried about the entire line now. Now I just want to talk about the segment from the center to that perpendicular bisector. So I'm going to hide my lines, and we can just talk now about the segments CI and CH. Well, I know that they bisect. So if I put my triangles back out here, and remember, these chords FG and ED are both congruent, so these are the same measure. I just proved that this triangle is congruent to this triangle. Triangle CEH is congruent to triangle CDH. What about these triangles? Well, I know that this is a bisector. For the same logic that I used over here, we could show that triangle CFI is congruent to triangle CGI. But not only that, these are congruent chords. So if I know that this segment is congruent to itself, and this segment IG, is congruent to IF, and this segment's a radius, so CG is congruent to CF, this triangle is congruent to this triangle. But more importantly, if I know that this chord is congruent to this chord, then I know when I bisect it, this segment, FI, is congruent to segment EH. There we go. IF is congruent to EH. And I also know that this central angle is congruent to this central angle. But this central angle is also congruent to this central angle, and by the properties of isosceles triangles, this perpendicular bisects this angle. So these angles are congruent as well. This angle is congruent to this angle. This angle is congruent to this angle. Angle ECH is congruent to angle FCI. This is a radius. This outside angle is congruent. So by angle side angle, I know that this little triangle, triangle FCI, is congruent to triangle ECH. If I know that's true, then that leads me to my fourth property of chords. If I have two congruent chords, then this distance, the distance from the center, is also congruent. So here segment HC is congruent to segment I see. Every time, if the chords are congruent, the perpendicular bisector from the center to the chord will be the same measure. Or more generally, the chords will be equidistant from the center. All right, so now let's review really quick. If I have congruent chords, they define congruent central angles, and they intercept congruent arcs. And if I have a perpendicular line from the center to a chord, it bisects the chord. Well, let's say for a minute that I have a circle. But when I'm looking at this circle, I don't have a clue where the center is. How can I find it? Turns out that not only is a line from the center to a chord perpendicular, but if I were to draw a chord anywhere on this circle and then construct the midpoint and a perpendicular line through it, so I just made, here's a perpendicular bisector to chord JK. Where do you think this line passes through? Well, it's perpendicular and it bisects a chord, so it must pass through the center. But I don't have enough information right now to help me figure out exactly where that center might be. So what do I do? What do I do? Well, if I can make one chord, can't I make two chords? And it's critical to show you that it doesn't matter how big this chord is. Any chord, I can find the midpoint, and then I can make a perpendicular bisector through it. It's going to pass through the center. Look at that point of intersection. It doesn't matter how I change this chord. If I make it bigger or change its location, the perpendicular bisector always intersects the other perpendicular bisector at the same point. So let's put that center back out there. Look at that. Always passes through. So if I don't know where the center of a circle is, I can make two chords on the circle, find the perpendicular bisector, and it's going to pass right through the center. And just for fun, let's make a couple more of these things. If I make a midpoint, and then I find the perpendicular bisector through it, it passes through the center too. Doesn't matter how big or how tiny, it always goes through the center. So my final property for chords is that the perpendicular bisector of a chord always passes through the center. All right, so now make sure you go back into your book again, check out your conjectures that are listed in section 6.2. Make sure you fill them in with the knowledge that we just learned, and then that will equip you to knock out the homework for section 6.2.